Welcome to my lecture again. We will continue on chapter 3, which is on the lexical analysis and scanner generator. In this chapter, we have looked into what is a formal language. We also have looked into a lexical token. We also looked at implementations using a finite state machines. So for this lecture, we will look into what is a lexical tables and as well as a lexical analysis with a scanner generator. So for creating lexical tables, this is actually the important output from the lexical analysis phase, the first phase of the compiler. Okay, so this is actually the important part, the lexical table. So this table actually includes a symbol table for identifiers, a table for numeric constants, string constants, statement labels, and as well as a line number for language. For example, like a basic. Okay. So the organization and implementation technique of this table will include a sequential search, binary search tree, and also a hash table. So when we have a table of informations, the table that contain a data, we need a certain way in order to process the data. So in this chapter, we will look into how are we going to organize and process our data in the tables, the information that we entered into the tables. So there are three that will be discussed in this topic, which is sequential search, binary search tree, as well as a hash table. So the first one, sequential search. Okay, the table could be organized as an array or linked list. We normally heard this term sequential search when we learn a data structure. Okay, so we have this kind of search in an array or in a list. Okay, so every new word is scanned in this list, and if the word is not encountered, so it will be added to the end of the list. So every new word will be added at the end of the list. So the data inside this list is actually unique. So before the data is entered into this list, the data need to be scanned first to check whether the data is already exists or not. If the data is not in the list, then the data will be added to the end of the list. Okay, so time required to build a table of n words is n squared. So that is the time required. Easy to implement but not efficient when it comes to a large data. When the data is too large, it requires more time to process. So it is not actually efficient but easy to implement. So this method is generally not used for symbol tables because it's quite large informations, or table of line or tables of line numbers. Okay, but could be used for table of statement labels or constants and declarations because the information is not many. So how do this sequential search work? So normally you will have a data will be inserted in a form of array like this. Okay, so the data the data will be, the searching will be start from the first locations. So it start to compare between the first data and the second data, and the data that you get will be compared to the next one and next one and next one. So the process will be repeating, and this is the first phase. On the second phase, they will start by the second locations, and again they will compare it again to the next one, to the next one, and to the next one. Okay, that is second one. So imagine if you have hundreds of data, so this process will be repeated 100 times. Okay, so that is on sequential search. What about a binary search? Binary search is more efficient. Okay, so for initial to start, when you start doing your search, the tree is actually empty. Okay, actually empty. So the first word will be placed at the root. So for example, this is the root frog and a bat. So the first word will be placed on the root. Okay, then we continue with the second word, third word, fourth word, and so on. So how are we going to insert that word in this tree? So each time a word, we say W encountered, we have a word W, it will be compared to root. So we need to, every time we have a new word, the new words need to be compared to W. To a root, which in this case is frog, in this case is bat. So how does it work? If W is smaller than the root, it is placed at the left subtree. So for example, how do you know? If it is number, we know it is smaller or greater. But if it is a form of letter, how are we going to know whether it is smaller or bigger? So it will be based on the ASCII code, ASCII number. Okay, so for example, in this case, we know that between a frog and bird, B will come first before frogs. So the value ASCII number for B is actually smaller than frogs. So bird here will be placed at the left subtree. Okay, and then come another word tree. So tree, T will be greater, the ASCII number for T will be greater than F. So 3 will be placed to the right of the subtree. And then it continues with the next word. The next word will be compared to the bird, the next superclass. Okay, so B the same with B on the bird, B bat and B bird is the same. Then they compare with the second token, second alphabet, okay, I and A. So A is smaller. So when A is smaller in terms of ASCII number, so it will be placed on the left subtree. And the process continue. Okay. So this process is repeated until W is found in the subtree. Okay. When you do a search, then they will search it in that way. Okay, so until the word is found. If the word is not found, so until we have reached at the end of the leaf node, okay, wrong spelling, N-O-D, then the W will be inserted at the leaf node. Okay, so if we already searched through all these the leaf node, if the word is not found, then the new word will be inserted at that leaf node. Okay, so the time required to build such a tree of n word is n log n. So in the best case, the tree is balanced. So this is a balanced tree. This is the best case. Okay, but if it is not balanced, so it requires n squared. This is n squared. So this is the worst case. B is the worst case where it is not balanced. Okay. Okay, the third technique will be the hash table. So it can be organized as an array, okay, so like this array, or as an array of linked lists. So it means that we have several array here, array of 6 locations. So each of this array, each of this location will have a linked list. Okay, each of it will have a linked list. That is array of linked list. Okay, so it will start with an array of a null pointer. So this is all is a null pointer. Okay, then it become the head of the linked list. Okay, so this null pointer become the head of the linked list. A hash function is used to determine where to store the word in the list. So how do you know that where to store it? So we're using hash function. Okay, what is hash function? Hash function is calculated using this formula. Size of word, okay, size of word. In this case, for example, tree, T-R-E-E, the size is 4. H-I-L-L, size is 4. Bird, B-I-R-D, size is 4. Cat, the size is 3. That is the size of the word. and then plus the ASCII number of the first letter. So we need to know what is the ASCII letter for T, what is the ASCII letter for H, ASCII letter for B, and ASCII letter for C, and other words as well. And this is not percent, this is modulus. Okay, modulus would mean that remainder. What would be the remainder? After you divide it with array size. So in this case, the array size is 6, 0 up to 5. So the size is 6. Okay, so that is the array size. For example, I take the word frog. What is the size of frog? Size of the words frog is 4. The ASCII number of F is 102. So the array size is 6. So the calculations would be 4 plus 102 divide by 6, and you took the remainder. So in this case, the remainder is 4. So frog will be placed on the fourth location 4 here. So that is frog. Okay, and the rest will be based on what the remainder they get. For example, like tree, hill, bird, and cat, they all are 0, 0, 0. The remainder is 0, so they are put in the linked list of locations 0. That is a hash table. Okay, so that is the tree implementation technique for manipulating or inserting or processing data inside the table for a lexical analyzer. Next, we want to look into a lexical analysis with scanner generator. So scanner generator is a program that created by the programmer in order to generate a compiler. Okay, so we look into a scanner generator. It says that it is a utility program that could help in lexical and syntax analysis. Okay, that's a scanner generator. So in unique environment, we have LEX is for lexical analysis, and YACC yet another compiler. Okay, so this one YAC is for syntax analysis. So this utility program actually is to generate a compiler from a set of specifications. So we need a rules like we learn in finite state machines. So there is a specific rules. We have a token as well. So we have a specification that will be inserted into this scanner generator. So other example of utility program, we have lots. So that will be the earliest one, Lex and York. So we have like a JLEC, which is Java lexical analysis. Okay, for lexical analysis, we have a curve, constructor of useful parser. We have LR, another tool for language recognitions. Okay, we have Java CC. This is from Sun Microsystem. So this is the most widely used utility program. And also SableCC. This is from McGill University. So in this lecture, we'll be introduced to SableCC. Yeah. So for SableCC, we will see some features of SableCC. SableCC is designed to make good use of advantage of Java. So SableCC actually is from a Java language. So it is, because this is a Java language, is also object oriented. Okay, so we can make an inheritance out of it. With a SableCC also, compilation error are easier to fix. Okay. It also generates modular software, which is each of the class in a separate file. We can have that as well. Also generate a syntax tree. SableCC, they can have two functions: analyzer, lexical analyzer, as well as a scanner analysis, which is the first phase and the second phase of compiler. SableCC also can accommodate wider class of language than JavaCC. Okay, so it also permit LL1 grammar. So this LL1 grammar, we will look into this topic on our a few more topics, a few more lecture. Okay, so this is just an introduction of SableCC. We will see how we can process and run tutorial using a SableCC in a few chapter after this. Thank you very much.